All right, we continue our discussion on what are properties of nanomaterials. How do we define nanotechnology and what makes up nanotechnology? So today's quote, it's not that I'm so smart, it's just what I say with is it's just that I stay with problems longer. So we many times we give up. So that was Albert Einstein who said that he spends a little bit more time than others on the problems at hand. So more so that what we'll be doing a little bit more time on ideas that we explore going forward. We'll continue on the basic concepts of nanotechnology. So today what we're gonna see this how nano world affects us, or what are the properties at nanoscale which are different than large scale, and what are their impacts on what we do now. And when we say we do now, we have many products or many inspirations that have helped us. It's just an example of animal world or insects. So we see uh, many insects. They can stand on water like mosquitoes, right? So now seen we have the ability to look at their feet, and what we see nano grooves or nanoscale features on their feet, which give them hydrophobic property, and hence they can stride on water, they can walk on water. So at the end of the day, this is all about nanoscale properties and things at nanoscale that we didn't have a way to look before, and now we can. Now, when we say we could see those things now, there are many more things we can build ourselves. And that's the goal of today's lecture, that how uh, things at nanoscale are different and what makes them different. So I've listed a few here that we'll go through. First of all, for the number one is self-assembly. So self-assembly, the cartoon shows that there's a very small nanotip that has some molecules that are in a liquid. So wherever the tip goes, it can, like an ink, it can write those molecules. But there's something special. In this cartoon, it shows that those molecules, which are shown as green and with the pink head, they would line up. They would align when they're put down. And that's essentially what we call self-assembly. In the lower cartoon, they've shown that if you throw some molecules, and this is not random now, this is engineered molecules where we know their properties, we know exactly what kind of properties they would have, and they can assemble in solution. Once they can overcome the movement, they can, and there are certain forces that are involved, they can assemble into predefined shapes that we define for them. How does self-assembly work? We design these molecules in a way that uh, we make one end to be uh, in a tail group. We call it tail group. This is shown as in red. So that can be what you call that binds to the functionalized surface. And then we put some alkyl chain, which is carbon chain, and they can bind to the surface. Now the gold side shown is there are simple examples like this can be a thiol, which is gold, and this can bind, sorry, the thiol is SH3, sulfur hydryl group, and this can bind to gold. So if you were to make an assembly, and there are so many different ways how you can design your self-assembled monolayer. Once you put them down, the thiol, because it has more affinity to gold, this would align the molecule that only the gold side will be down, and the other side, the functional group, will be on the other side. And this is a very well used way where we put molecules down. For example, we put nucleic acids, DNA, or proteins as well, or antibodies. And what we achieve when we do self-assembled monolayer, we can functionalize surfaces to have specific properties. So by definition, it would be, it's the process of self-organization of one or more entities. But how it happens, the overall total energy of the system has to come down. So that there's an energy computation which makes things happen, that they follow and they fall in place. So in solution, those molecules would be random. I should have made it a little bit more random. In the upper figure, they show that molecules are aligned there. They can be floating around in either any direction. But once they come to the surface, they would all line up and form uh, very fine arrangement of molecules. And there are few things that need to happen when we call it self-assembled monolayer. We have to have some movement for them. So it can be diffusion, it can be drift, it can be forced pumping, mechanical pumping as well. It can be, we can have a particle which responds to electricity, right? Electrically conductive. It can be a magnetic particle. So there are many different ways how we have been able to move them around and bring them where we want them to go. Once they come close to the surface, there has to be a chemical affinity, what we call a recognition. So recognition, we'll talk more when we talk about sensors or biosensors, because unless they have a specific binding, they can randomly go everywhere. So we engineer them to have a recognition between two elements. And then once they get there, then they have to overcome forces at that, uh, now it's essentially nanoscale, molecular forces. So they have to be able to overcome those forces. And those forces are electrical forces, van der Waals forces, it's covalent bonds, ionic bonds, hydrogen bonds. So these forces are building blocks of self-assembly, right? So now we don't encounter these forces in large scale. We encounter them at small scale. So these are, when we deal with larger uh, mass micro scale things, we ignore these forces. But when we are talking about few molecules or molecular level interaction, these forces become significant. Now, when these forces are there, we have to design, we have to calculate how much force, how many what would be the magnitude, and the engineer design has to be made in a way that we overcome those forces. All right, we'll talk more about nanoscale forces. There's one thing which you will see is missing is gravity, right? So there is a size domain below which gravity becomes insignificant, and we use that to our advantage. That's another nanoscale property which is important from us, and we'll talk more about that today. Another important property at nanoscale is superconductivity. Superconductivity is a holy grail. This is superconductivity has major implications in electrical devices, all the electrical systems. Superconductivity has major implication in military applications. So we do achieve superconductivity, but we achieve superconductivity in special materials. And we have to cool those things down to very low temperature to achieve superconductivity. So the goal is, if we can achieve superconductivity at room temperature, or relatively, we don't want to cold our things too much. So that's a major challenge. Now, if thinking about it as electrical engineer, we know the size of conductor has size. When you say size, it's the length of the conductor and the area of the conductor. They have relationship with the resistance of a conductor. So we have a relationship R equals rho L over A. Rho is, so now L over A, area, when you make the area smaller and smaller, what happens to resistance? Rho L over A. Resistance goes up, right? Now, how do we then achieve superconductivity? So that's the phenomena where we, instead of making it a one-dimensional, we work with thin films. So we make a two-dimensional thin film. So we achieve huge area, right? So there the physics of big conductors then fall down, then breaks down. And one very important example of superconductivity in nanomaterial is graphene. We'll talk about graphene specifically later on. So that's another property at nanoscale, which is distinctly different. All right, optical properties. So how do things transmit light, color? So we know that every system, especially semiconductor systems, have a band gap. And the band gap results into very specific wavelength that's emitted. We'll not go into band gap at this stage, but what I want to say is that crystalline semiconductor materials emit very specific wavelength. But the same material, if we chop it down into smaller size, same material, which is supposed to emit one wavelength, by tuning its size at nanoscale, we can make it emit different wavelength, hence different colors. And those are called quantum dots. So here's an example of cadmium selenide, zinc sulfide quantum dots. Same material, but when we make the nanoparticle of this material smaller size and we keep on reducing the size, we can achieve different wavelengths coming out of that same material. That's another property of nanomaterials. We'll talk about quantum dots as well once we get into the nanomaterials part. But for now, I was hoping that we can see that there are special properties, hence special electrical, mechanical, optical systems or equations or models that we need to learn and adopt. And, and then we use them in applications, for our case, for bio applications. Now, with there's another aspect to what we just saw is when you make them too small, they don't have effect of gravity on them. Hence, this solution of quantum dots, they will always stay dissolved. They will not settle down. We know if you dissolve a, a solute and you create a solution, if you leave it long, things can settle down on the surface, right? After some time, they will settle on at the bottom, but not for nanomaterials. They will forever keep on diffusing around in the solution, hence what we call that they don't have effect of gravity. And we call these solutions colloidal solutions. Colloidal is a term from colloids, very small particles that would not settle down. They may, if there are forces that make small particles come together and they become bigger and bigger agglomerations, then they would become thick enough or bulky enough that gravity will start having effect on them. And then they can settle down, right? So, but we do some tricks there also. When we have a nanomaterial in a while, we put some chemicals in there. We call them surfactants. They cover the surface so they can not settle down. So far with me, all of you? All right, I got a question. Musa says the change of color does no have effect. The change in color is result of the nano properties. The change in color of the same material is because we keep on making it smaller and smaller, and we make the size so small that we start messing with the band gap of material. Band gap. Let me just go back to basic chemistry. You guys remember we have valence band in an atom, and then we have conduction band. The electrons have to jump from valence band to conduction band for reactions or for becoming available for conductivity, right? So that difference from valence band to conduction band is what is called band gap. It's an energy gap. Now, if we make these particles so small that we start messing with the band gap, basically the band gap is what defines the wavelength. It's inversely proportional to the wavelength. So if we physically we're not physically directly changing the band gap. Band gap is an energy property, but the size results into a property called quantum confinement. Another concept, another topic, but that quantum confinement results into the particles showing different wavelengths, showing band gap engineering. Yeah, Mats, go ahead.
Sir, my question is that can natural effects like temperature any effects on these nanoscale devices, sir?
We are getting there. Yeah, we'll see that. Yeah, we are good question. Just wait with me for two more bullet points and we'll talk about how the reaction or how temperature effect would be different if we chop a material into nanoscale size. Right? We'll see that. All right. So this is we're talking about nanoscale and optical properties, how optical properties are different and what would happen and colloidal solutions for that matter. Another interesting property, wetting. Wetting is every surface has some wettability, and we measure that, we quantify that in we have qualitative way we can measure them, we can have exact numbers about the wettability as well. But generally what we see is if you put a droplet on a surface and if it is hydrophobic, the droplet stays like a drop. But if it is hydrophilic, the droplet spreads, water spreads. So that concept is called wettability, or what we call technically hydrophilic and hydrophobic material. Yes, Ahmed, go ahead.
Yes, sir. I want to ask. So in like your in the Feynman talk, it says that we could, he states we could like write the entire library on a type of pin. So does that concept use self-assembly? So is it related to self-assembly?
It,
So
it
that
can be it can be self-assembly. Yeah, if you can use self-assembly to write zeros and ones, think about it. That zeros and one binary, we can code that information as binary, right?
okay.
So that's an interesting way to look at it. Yep, I agree with you. This could be so if we can address very specific points in that self-assembled layer, then we can say if there is a molecule or if there is not a molecule that can be taken at 0 or 1. If you can find a way to read it as 0 and 1, that's your digital data right there. And then we can use
Okay.
digital to code our information, right? Like we do in
Okay.
digital systems anyway. Very good.
Okay. Thank you.
All right. So hydrophobic or hydrophilic. Philic is water, right? What? Sorry, hydro is water, and phobic. What does phobic mean? Phobia. When someone has phobia, what does that mean? People have phobia, right? We use this word in our everyday language. What does phobia mean? Afraid of. To be afraid of something, right? You guys can text, chat, speak up any way you like. But so phobia, hydrophobic means something that does not like water. So a surface can be hydrophobic. Give me an example of a hydrophobic surface. Give me an example of a hydrophobic surface.
Glass.
Glass.
Yes.
Think about you know when you get your car clean, washed, they put wax on the car surface, right? So they polish the car surface. And when you have your car polished and everything, if you put a droplet, water doesn't stick, water just flows down. Water doesn't stay. But if you haven't got your car cleaned or a surface is dirty, you will see water will stick. Water will, clothing, some clothes get wet, some clothes don't get wet, right? If you are wearing a speed breaker, you know, the jacket, or maybe a leather jacket, the water does not seep in the leather, right? It just slips off the surface,
Oil, sir.
right? But a regular clothes, you may put the water and it will absorb water. Yeah, Ahmed, go ahead.
So
Like
what are some practical applications of wetting exactly
Will
in?
A very interesting question. Why would somebody want to wear clothes that don't get wet? Right? That's the question. I ask you, give me an example of a profession where people do not want to get their clothes wet. Give me an example of a profession where people do not want to get their uniform wet. Oops, I gave you a hint there.
But uh, crossing guards,
Soldiers,
soldiers now.
right? When you're deployed, if a think about it, if a soldiers are deployed in desert, in water, their socks get wet, right? They need to change their socks. But what if their socks, their uniform do not get wet? Wetting is what causes the sweat to make your uniform look dirty, or the dust settles, right? You know, if the number one thing why we need to change our clothes is because they start smelling, right? Why do they start smelling? Because they absorb sweat. That's one interesting example. We
Um,
think about it.
Sir,
Yeah, go ahead.
yes, sir. So, is wetting different from applying sort of like hydrophobic coating on a cloth? Is it
There are
different from?
we can coat things with hydrophobic nanomaterials that can give them a property of hydrophobic, that the water will not stick, water will not absorb at all,
Yeah.
right? So that's another. Remember, I showed you the mosquito standing on water. That's hydrophobic property that makes those things stand on water. They don't drown, right? Have you seen a bird dip inside the water and catch the fish and come out? Why do not they get wet and soaky and drown? Think about it. What may be? Because their feathers are hydrophobic. They have been created or evolved, whatever you believe in. They have feathers that are super hydrophobic. They don't get wet. They jump in, they get their food, they get out. So that's another natural phenomena where we see uh, hydrophobic. And I gave you examples of insects which have nanoscale features on there, right? So we are trying to learn and try to build similar things that can have those properties, all right? So here are examples, stain resistant clothes. So your car, trust me, if your car body is hydrophobic, water will not stick, which means no mud will, if water doesn't stick, your mud will never stick because everything gets on the surface of the car with water. Water dries, soil remains. What if water doesn't stick? Nothing will stay. So that's why they do the waxing of the car, right? What do you call taki marta ladka polishing? So that's what the wax does. Looks shiny, makes it hydrophobic. All right. So that's
Plastic is also hydrophobic.
plastic is hydrophobic. Fantastic. So think about it. They put the wrapping of plastic on food when they packaging. Why do they use plastic in food packaging? They don't want water to stick or water vapors to get through or to get to the food because that would create mold. That will create things to go bad. So packaging, yeah, packaging is a big industry in nano where they want to come up with packaging where things don't stick. All right. All right, let's continue. So reactivity. So something very interesting, and these next two, three concepts are interconnected. What I just want to say is, look at this blue and red thing, right? So if it's a big chunk, big block, and if I do a reaction, give me an example of a reaction. Do you guys from everyday life reaction? Or just give me an example of a solution where things dissolve. Chai.
Well, sugar in water, but
Sugar in water. Yes, Ahmed, I like you, man. You have all the good examples today for us. sugar in water, right? So you get bigger chunks of sugar, what they call shakkar, I think, or in Iran they use kand. It's a big cube. You put the cube, it takes longer for it to dissolve. Now you crush it and you put it dissolves right away, right? So same mass, you put maybe I don't know, 100 gram of a cube and 100 gram of that cube ground into a powder. Which one is going to dissolve first? The powder,
Powder forms.
right? That's reactivity. If we cut things down into smaller pieces, they would react much faster. They would dissolve much faster, but if there is a chemical reaction we want to do, they would react much faster. Now, think about it. When we cook, are there any men cook in this room? Ladies, I know ladies, many ladies know how to cook. So we put some things which are powdered. We put some things which are not very finely ground. We put some things which are bigger. They all have to do that. We need to have some things dissolve right away. Some things need to give their juices slowly, and some things we need to like stay intact up to the last time, up to the end of the cooking, whatever it is. So all these things, they have a reason. We have learned by crushing things into smaller pieces that reactivity is much different. Same mass, reaction would be different. On the right hand side, I'm showing a picture of carbon nanotube. Now, every atom of that carbon nanotube is available for reaction, right? Think about it. If you put carbon nanotube in a solution for some reaction, each carbon is there for reaction, binding, whatever we need to achieve. But if I have a big chunk of carbon, give me example of big chunk of carbon.
Diamond.
Diamond is very expensive. Ahmed, you are a rich man. Give me a cheap example of carbon.
Graphite.
Graphite, right? Charcoal, coal, koila. That's you burn the bigger piece, you burn a smaller piece. You know the difference. Now, a carbon nanotube or a graphene sheet or a buckyball, we'll talk about those also, C60. They have each carbon atom available for reaction, hence different properties. Now, when we are talking about this crushing things into smaller pieces, this is called surface to volume ratio. That's the terminology that explains that concept, right? What is surface to volume ratio? I take a big chunk, I can cut it into a small piece, I can cut to smaller piece, I can cut it into smaller and smaller pieces. Hence, we are going from center to left, to the right of the screen. What is changing? The volume is the same, total volume is the same, but the exposed surface is going up. You agree with me? Let's do some exercise. Everybody make a big cube on your paper. Make a cube on your paper. You have a paper and pencil with you? Okay, let's think about it. Let's take a cube. And I say this cube is 1 inch by 1 inch by 1 inch. All right? You with me? What is the total surface area of this cube? Can somebody tell me what is the total surface area of this cube?
18 square.
18 square inch? Guys, it's one cube. Each side is 1 by 1 by 1 inch.
So 1 meter, one.
Okay, I gave
1
you a
meter
cube.
cube.
I gave you a cube. I said each side is 1 inch by 1 inch by 1 inch by 1 inch. Sorry, just 2 dimensions. You need 2 dimensions. Each face is 1 by 1 inch, right? What is total surface area of that cube?
It has to be 6 because there are 6 faces.
Yeah, Ali, you're right. Ali, why do you have to be so worried? It is 6 square inch, right? Somebody write down somewhere 6 square inch. Now I said chop it into 2. Now I have 2 rectangular blocks. What is the surface area of one of those?
6 square inch.
Dude, take it. No, it's not 6 square inch. Let's calculate. One, I said, this is what we are doing here. This second one, let me mark what I'm asking with. So
total become 12.
I said, okay, I said this is 1 by 1. Now I say chop it into, what is the surface area of this guy? Just this guy. So
3.
this would be 1. This would be half times 1, which is half. And there are 4 of those, right? And the lower side, which is not visible here, would be also 1. So what's the total?
6.
1 square inch, 1 square. Dude, it's not 6.
4 square inch.
4 square inch. Who said that?
Me.
Just say your name. Me is like
Shahram.
Sharam. Yeah, Sharam is, you got it right. So if I clean this page and now I say this was 6 square inch and this is 4 square inch, which means the total surface area now of the same volume is what? 8? It has gone from 6 to 8. Do you see what I'm saying? In numbers, just by making it half has made it go up by 33%. This is 33% increase. If you trust me on that, I've taken GRE long time ago. 1/3 of these 2, yeah, 6 plus 2, 1/3 is 33% increase. And you keep on chopping it smaller and smaller. For the same volume, surface area keeps going up and up. Capiche? With me on this? I don't know. Capiche is Italian for, I don't know. You got it? All right. Sorry about that. So, okay. So now I take you to simple calculation. So here I say, okay, we start with the big cube. It looks like Rubik cube. You know what's Rubik cube, right? Rubik cube, you know, they change around, they put the colors, all the colors on one side. Now, if I take sides, I calculate the surface, I get surface to volume 2. I take 2 sides. So you keep on playing, you see the smaller and smaller we go, the surface to volume ratio keeps on going up and up, right? The surface to volume ratio keeps on going up and up. Just another way of looking at the same concept. So what we are saying is, one thing, let me go back. One thing is that you have, since we have much more surface area, we have many, many more atoms now available for reaction, right? Surface. When you have a big cube, reaction always starts from the surface, right? And then it keeps on eating away and keeps on going. But if you have all the atoms there, your reaction will be really, really quick. Okay, so now what does it mean when you have very small size? We can either fit many nanoscale things together with little space between them. We can have large number of things and put them in a small number of volume. So there are different ways how we can do this. Or we can just get large number per area. So when we talk about a very large, a very small size in nanotechnology, it may not be one material that we have chopped into a small place. It may be other types of materials, but nevertheless, the goal would be to make things that are highly reactive or highly, when you say reactive, it can be burning, it can be melting, it can be whatever happens with those molecules being available on the surface. All right. Now, to put this little bit in mathematical perspective, so you take surface for a globe, for a sphere, it's 4 pi r squared. And you take volume is 4 by 3 pi r cubed, right? You agree with me on the simple formula? Right? High school maths. So we can just get the ratio, which is 3 over R. Okay? So R goes down, the ratio goes up. Right? So this ratio becomes very large when R becomes very small. All right? Why is that? Because when you divide something with a fraction, the total number goes up. When you, okay, this is again a simple concept. That if you divide something with the, let's say, x divided by y, if y is greater than 1, this ratio will become smaller and smaller, right? What if y is less than 1, which is fraction? When you divide something with a smaller, when you divide something with 0.5, what happens to the quantity?
Actually, it depends on the value of x as well. I mean, if x should be small as well.
Okay, Ali, let's take any x in the world. Let's decide, say we take 2. You divide it 0 with 0.5. What happens?
It's going to get large.
Dude, give me the number.
By 4.
2, 4, right? It just doubled.
Yes.
2 divided by 0.25. Nawal, give me the answer. 4 divided by 0.25.
16, sir?
Are you Nawal?
Oh, sorry.
It's okay. 2 divided by 0.25. Guys, you have calculators? Yes, sir.
It's 16 actually.
Yeah.
2 divided by 0.25.
8.
8.
Guys, 8. You guys have cell phones? Cell phones have calculators, you know that. All right, I'm just pulling your leg. All right, yeah, I got some answers. 8. So think about it. If you keep on making the number, the y smaller and smaller, the total number is happening what? Bigger and bigger. Ali, Myra, Amina, I cannot see you and I have no idea if you are with us or not. But you got the idea?
Yes, sir. Assalamualaikum. I'm Amna. I'm here.
All right.
I got the idea.
Yes, sir.
Yes, sir. I'm also here.
I
Get
answer in chat.
All right. Very good. So now, what are implications of this? Implications are many. There's one example that there's an inverse relationship between particle size and number of surface atoms. So this picture from 2006 paper is just showing that if your percent of surface atoms, if you make the diameter smaller and smaller, what's happening here? The number of surface atoms. Can somebody tell me what kind of function is this?
So it's exponential decaying.
exponential.
Function. Amna, you are 100% right. So they are exponentially, these surface atom, number of surface atoms are coming higher and higher as you are breaking, chopping the material down into smaller and smaller pieces. Right, Ali? Something, it's enjoyable, right? This is the amazing world of nanoscience or nanoparticles or nano world, because they have implications on what can we achieve with them. And once this happens, their chemical, biological, physical, electrical, I don't know, all the optical properties change. And we can change them just by doing what? Just by changing their size. Going from, think about it, going from, this is logarithmic scale. So going from maybe 11 to 10, let me take, there's change from here to here, right? Which is a big change on y-axis. Are you following what I'm saying? From here to, so very distinct, very small change in size and big change in the number of atoms that may be available. All right? Okay, big deal. Just think about melting temperature to start with. Melting temperature, we make particle size of gold small and it falls down, again exponential. Now, if you are a, what is it called, goldsmith, you want to save money on burning for heat to make your whatever gold. I'm not saying you, if somebody was goldsmith. So there's benefit of less energy required to melt things if they are small. Hold on, let me clear this came from previous picture. And that has implications. We'll talk about chemistry later on, but it has the similar concept of chemical reactions. It has similar concept of biosensors, which ultimately will be going there, right? I'm trying not to scare you so early with biology. We want to see small number of molecules that exist in living systems. We want to see small change in the concentration of those small number of molecules, which is a bigger task, right? So for that, we need to have smaller entities that can show small change in whatever phenomena we are looking for. Make sense? That's the strength. That's the ultimate goal that we have. All right, questions. Let's go back. There's one more thing I wanted to slightly emphasize. Yeah, chopping it into smaller pieces results into many, many different properties. All right, Hamza says, we differentiate crystal based on a sharp melting point, but it seems variable now. Exactly. In the nano world, it is a variable, Hamza. You are 100% right there. All right, questions? No questions?
Sir,
Sir, what is a variable? You said what is a variable, sir?
One at a time. Hold on, one at a time. When they're okay. Who wants to go first? All right, Emma, go ahead.
So you were saying, could you repeat it? What is a variable exactly? Surface to volume ratio in what?
It is variable. No, it's
Yes.
not a variable. It depends on the size. In
So,
nano,
no, you answered somebody's question that it's a variable.
okay, somebody asked that we differentiate crystal as a sharp, but it seems variable now. It is because when you go smaller and smaller, the number of atoms that are available exponentially change below certain size. So it up to certain size, you wouldn't have a dramatic change in the number of atoms that are available for reaction, for melting, for whatever process or things we are doing. But beyond a certain size, what kind of relationship is this?
Yeah, the variable in
Exponential.
exponential. Yes.
If you remember exponential functions, you
Yes,
know
exponential. Sorry.
they dramatically change and they're asymptotic. Asymptotic, maybe I shouldn't go there. It's
So, what other impacts are there of a huge surface to volume ratio besides chemical and biological properties?
everything is different at nanoscale. You take one material and you are used to of doing things or whatever properties. Nanoscale, you have to go totally use other sets of equations or models to understand them or to use them in whatever research or application you are doing.
Okay.
Yep. All right. There's another question.
Sir, okay, sir, I can wait.
All right. Is it Aruma who's talking?
Also, it's Amna.
Amna, go ahead, Amna.
Yes. So sir, I believe doesn't it get things get more difficult when we scale down to nanoscale?
Of course, that's why we are. That is exactly why we have this course, to make those difficult things easy for you.
Okay, sir. Thank you.
Right. This is a whole. It is a totally different science there, right? The laws of physics, laws of the relationships, the energy issues, forces, they all change. They all are different. So yes, you are right. That is why we are talking about these properties, that they're different at nanoscale. right?
Okay, sir. Thank you.
All right, Ahmed.
Sir, my question is that why we just improving like in electronics component, just improving the transistors, sir? Why not other components like resistor or capacitor, sir?
Why we do what? Okay, what's the question?
Why we just focused on transistors, sir?
Okay, so think about it. In a logic circuit, what is at the heart of it? It's transistor. It's a variable resistor. So now a resistor is a two-terminal device. You have a region, you put two connections to it, and you know what's a resistance. But a transistor is a three-terminal device. You have interesting things happening where you have source and drain, and then you have a gate area. You have to control the gate. How close you bring source and drain, how thin you make the gate dielectric, that is the difficult part. So making resistances, capacitances are slightly easy than focusing on transistors.
Sir, my second question is that can nano technology any effects on powers electronic side, sir?
Power electro, oh, all the circuits, all the ICs, they use solid state materials. They use solid state devices. They use semiconductor materials in there. So their fabrication, their uh, packaging, that's all where we are using new materials. We are using new approaches to make those things. Yep. So everything is getting affected because you can employ newer properties of the same materials that we are using before. Right? All right. Questions? All right. If there are no questions, let me do a couple of things.